In this video, we're going to look at zeros of polynomials and polynomial inequalities. We rely heavily on that zero product property to solve polynomial functions. The zero product property says that if you've got the product of two terms and that product is zero, then one or the other or both have to be zero. Remember that a quadratic equation is exactly a polynomial. It's just a polynomial of degree 2, but we usually do separate quadratics from polynomials because we have a few rules that apply specifically to quadratics. So let's just do a quick review of quadratics. We've seen this many times in this class. You've seen it in previous classes. So this hopefully is a nice review. The general form of a quadratic equation, y equals ax squared plus bx plus c. We know the graph of a quadratic is a parabola. Parabolas are symmetric about a line of symmetry that goes through the vertex. That parabola being that U-shaped graph, so it can open up or it can open down. We can find the vertex, which is the maximum or the minimum, depending on the orientation of the graph, 3 different ways. We have a formula for the vertex where the x-coordinate is negative b over 2a, and then the y-coordinate is where you just plug that value of x into the function. And that b and a come from the coefficients from that general form. We can put the quadratic into vertex form, y equals a times x minus h squared plus k. We do this by completing the square. The vertex is then the coordinates or the ordered pair hk. We can also use technology to find the min or the max, which is that vertex. We also refer to the zeros of a quadratic all the time. We can find the zeros, which are just another name for your x-intercepts, by factoring and using the zero product property. That's our very most common technique for finding zeros. We can take the square root depending on the way that the quadratic is set up. We could complete the square, which then does also involve taking the square root. We can use the quadratic formula or we can use technology. So in this first example, we're going to just practice finding the vertex of our function using a few different methods. So our function is f of x equals 2x squared minus 12x plus 19. We're going to find the vertex using the vertex formula by completing the square and using technology. So the vertex formula, our x is equal to negative b over 2a. B in this case is negative 12. So negative b would be positive 12, and a is 2. C being 19. So this is going to be 12 over 2 times 2, or 12 divided by 4, which is 3. So the x-coordinate of our vertex is 3. To find the y-coordinate, we're just going to substitute 3 into our function. So we've got 2 times 3 squared minus 12 times 3 plus 19. Now you can type this into your calculator, or you can simplify before adding it in, adding the terms in your calculator. 2 times 3 squared is the same as 2 times 9, or 18. Minus 12 times 3 is 36, plus 19. When we combine these, we get 1. So our vertex is the point 3, 1. Now we're also going to find the vertex by completing the square. So writing our function in vertex form. So we should get the exact same vertex. We're working with the same function. So f of x equals 2x squared minus 12x. And my first step is going to be to just move that constant down because we're going to add a new term here. So we want to make sure we have a little bit of space for that. One of the things I encourage you to remember when you are trying to complete the square is that you're not changing anything. So we have to make sure that whatever we modify to this equation, we modify in a way that we're not actually changing the original function. Now, the next step for completing the square, because we're going to complete the square for this quadratic and linear piece, we want to factor out that coefficient of 2. So we're going to factor that out from your x squared and your x term. So we have 2 times x squared minus 6x. And we still have the plus 19. Now at this step, we could see if we were to redistribute the 2, we still have the exact same original function. We haven't changed anything. We're just manipulating the way it looks right now. Now in this space that we left, we're going to add a new term, and that term is going to be b over 2 squared, but it's the b here. So it's going to be b over 2 squared. Now what we let me replace that with our value of b. So this is going to be negative 6 over 2 squared. Now we've added this piece here, this negative 6 over 2 squared, but that coefficient of 2 is going to eventually be distributed there. Since we've added it here, we want to also subtract it on the outside. So minus 2 times negative 6 over 2 squared. Again, if I were to redistribute this 2, we'd have plus 2 times this negative 6 over 2 squared term. So I also have to subtract it in this at the end so that I don't actually change that function. Okay, let's simplify. 2 times x squared minus 6x. Negative 6 divided by 2 is negative 3, and negative 3 squared is 9. So I'm going to keep this in pink just to illustrate what we've added here. Okay, so this, when we see it written like this, it's maybe a little bit easier to see why we've got the minus 2 times 9, because we're adding 2 times 9 right here with that 9. Now, x squared minus 6x plus 9, this is a perfect square trinomial, so this is going to factor to x minus 3 squared. And now we can simplify this 19, and this is minus 18, so this is plus 1. So now we have our function f of x in vertex form. It's 2 times x minus 3 squared plus 1. And our vertex is going to be the opposite of this constant inside of our parentheses and that value for y. So it's going to be 3, 1. Now the last step the last technique we're gonna use is using technology. So we're gonna go to Desmos, we're gonna type in our function. F of x equals 2x squared minus 12x plus 19. And it just so happened our grid's really set up nicely, the window's set up nicely, and we can see that that minimum is at 3, 1, which is our vertex. Now let's practice finding zeros of a function using these particular methods. So we're going to factor, we're going to use the quadratic formula, and we're going to use technology. Now we chose these 3 methods. If you recall from that list above, there's some other options. Taking the square root is going to just happen sort of organically. You're going to see an equation that's just set up to isolate x by taking the square root. We're not going to go through completing the square though, because while it is a technique that can be used and it has a place in writing our function in vertex form, and even when you get into some conics, trying to identify certain points in a conic, completing the square is absolutely necessary, but it's not really the most efficient method for trying to find the zeros of a polynomial or a quadratic in this case. So we're going to stick with factoring the quadratic formula using technology. So we're given the function f of x equals 6x squared plus 7x plus 2. So we're going to factor this. Now, I'm going to set up trial and error method. I'm going to walk you through that process. There's also the AC method, which is a really great method. And I can show you that after we go through the trial and error method. It's really up to you how you want to factor. I think at this point in the math curriculum, factoring is one of those skills that we just expect you to have, and however you do it is great. Now, you might have instructors that want specific methods, so just be aware of that. So I'll go through both trial and error and the AC method here. So my first two terms in my binomials need to be factors of 6x squared. So let's just try 6x and x. Now, the last two terms in my binomials need to be factors of 2. So the only options are 2 and 1. So if I do 2 and 1, that's going to give me a 12x and a 1x, which is not going to give me 7x. So I know that that's not going to work. So maybe we just switch the 2 and the 1. So now we have a 6x and a 2x, which is still not going to give me 7x. So I've exhausted all of the combinations with the 6x and x options. So now let's look at different factors for 6x squared. So we've got 3x and 2x. Those are the only other options. Now, for those last two terms, we still have factors of 2, which are 2 and 1. So we can do 2 and 1, which is, again, 6 and 2, which is 8. Nope. So let's switch those, 2 and 1. Now we have 3x and 4x. Ooh, there we go. Okay, so I think I found the factors. Now I'm going to practice or check my signs. So my the signs of my constants have to be the same because I've got a positive 2 at the end. So the last terms need to be either both negative or both positive. Since that middle term is positive, they should both be positive. And just double check. Quickly FOIL in your head. We've got 6x squared plus 3x plus 4x gives me that 7x plus 2. So there's my factored form. Now, to find the zeros, you're just setting your function equal to 0. So 3x plus 2 times 2x plus 1 equals 0. And the zero product property says that we're going to take each of those factors, set them equal to 0. We would get x is equal to negative 2 over 3, and x is equal to negative 1/2. And these are the zeros of that function. Now, when we reference zeros, a lot of times we just give the values of x. If they want the x-intercept, it's more appropriate to give an ordered pair. Just pay attention. The language can shift, but understand what's expected in terms of the answer and how it's represented. So a 0 of negative 2/3 has an ordered pair of negative 2/3, 0. And then 0 of negative 1/2 is negative 1/2, 0. So those are the ordered pairs for those x-intercepts. So let's review the AC method for factoring. The AC method is really helpful when we have a lead coefficient that's not prime, or just not a very low number. So 6, although 6 is not prime, there's still not too many factors of 6. So using the trial and error method like we just illustrated really isn't that time consuming. But if we had a lead coefficient of, let's say, 12, 12 has got a lot of factors. So we've got a lot of different possible combinations. Likewise, if we look at our constant term, the more factors that our constant term has, trial and error becomes very tedious because it could take us a while to land at the appropriate factors. So the AC method does eliminate a lot of that trial and error. So for the AC method, we're looking for factors of A times C that sum to B. So A times C in this case is 6 times 2 or 12, and B is 7. So here's the only part that's trial and error. So factors of 12 that add up to 7, that's going to be 3 and 4, positive 3 and positive 4, and those add up to 7. Once we have those factors, we're going to rewrite our quadratic. So starting with my function name, we've got 6x squared. And what we're going to do is we're going to separate that middle term of 7x using those two factors. So we're going to do plus 3x plus 4x plus 2. Again, observing the 3x and the 4x, if we combine them, we still have 7x. So I haven't actually changed my function at all. I'm just rewriting it in a very specific way. And now we're going to factor by grouping. So we're going to group the first two and the last two. 6x squared plus 3x, we can factor out a 3x, and we're left with 2x plus 1. 4x plus 2, we can factor out a positive 2, and we're left with 2x plus 1. And now both of those terms, separated by that plus sign, have a factor of 2x plus 1. And if we factor that out, we're left with 3x plus 2. So we see that we ended up with the same factored form as we did with trial and error. The AC method, again, just doesn't require quite as much trial and error. And it's a little bit easier to process since we're only looking for factors of one number that sum to another. So for me, in my classes at this level, you can really use whichever technique works best for you. Some students love the AC method just because it does give them a little bit more structure to their thought process, as opposed to the trial and error method, which does require sort of keeping track of what you've already tried. All right, so we're not going to finish that problem finding the zeros. Now that we see that we have the same factored form, we would find the zeros the same way. Now let's try using the quadratic formula. Quick review, the quadratic formula, x equals negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2a. Again, a, b, and c are the coefficients on of our quadratic. So looking at our quadratic above, we know a is our lead coefficient 6, b is the coefficient on x, which is 7, and c is our constant, which is 2. So we're going to plug these values in. We get x equals negative 7 plus or minus the square root of 7 squared minus 4 times 6 times 2, all divided by 2 times 6. So we have x is equal to negative 7 plus or minus the square root of, we've got 49 minus 48. So that's going to simplify to the square root of 1 over 12. The square root of 1 is 1. So this is negative 7 plus or minus 1 over 12. That plus or minus sets up our two solutions. So we have x is equal to negative 7 plus 1 over 12. Negative 7 plus 1 is negative 6 over 12, or negative 1/2. Or x is equal to negative 7 minus 1 over 12. Negative 7 minus 1 is negative 8 over 12, which is going to simplify to negative 2/3. So again, we have those same two solutions. Our zeros are negative 1/2 and negative 2/3, which can be written as ordered pairs as well. And then we can use technology. So we'll graph this in Desmos to find our zeros. Let's clear out our other function. F of x equals 6x squared plus 7x plus 2. So we can see this. We're going to zoom in a little bit further just so that we can see this graph a little bit better. And if we click on those on the graph, we can see that our first zero is at negative 1/2. And then our second one is that decimal point negative 0.6667, which hopefully you're familiar with that decimal equivalent, or decimal approximation, I should say, of negative 2/3. But those were the two zeros from Desmos. And again, that negative 0.5 is negative 1/2, 0, and negative 0.6667 is negative 2/3, 0. So that is one of the drawbacks of using technology. Oftentimes those values are going to be expressed as decimals. So if you're looking for exact answers, technology may not be your best option. Now, there is a note here. Sometimes our quadratic does not have real zeros. And in this case, it's not going to factor. So we have to use the quadratic formula in those cases. In a situation where we don't have real zeros, the graph of the parabola just doesn't cross the x-axis. So if I think about our vertex being in the first quadrant and it opening up, or something like this, where the vertex is in the fourth quadrant and it opens down. So we can see visually that neither one of these graphs crosses the x-axis, so there's no real zeros for this quadratic. In terms of if there's no directions on how to particularly find zeros, I always start with factoring first, especially if my coefficients seem workable. If I've got very large coefficients, I might not mess around with trying to factor, because then you're looking for factors of very large numbers, which, is just a lot of work, and maybe not something that would be very quick. So I might opt for the quadratic formula in that case. But if I've got workable coefficients, then I'm going to start with factoring. And if I can't factor quickly, then I'll jump to the quadratic formula. So that's just a quick aside on really what technique you should approach first. But ultimately, if there's no directions, then you could pick whichever method you wanted to try. All right, so let's shift into solving quadratic and polynomial inequalities. A big part of this is identifying the zeros, which is why we've gone through this process. So the first step is to set the inequality to 0, and then you're going to factor. So there is a note here that we might have to use additional rules to factor a polynomial if it's not like a quadratic or a polynomial of 4 terms, where we can use grouping. And we'll review some of those methods, those additional rules for factoring a polynomial in a little bit. Find the zeros. So it says specifically a quadratic, but it could be a polynomial. You're going to find the zeros, and these we're going to call our critical points. And you're going to set up a sign chart with your critical values marked, or your critical points marked. What this does is it sets up a number line into different intervals. At each critical value, you're going to mark it with either an open circle or a closed circle. We'll use an open circle if it's an inclusive inequality. We'll use an open circle if it's an exclusive inequality, so strictly less than or strictly greater than. And we'll use a closed circle if it's an inclusive inequality, so less than or equal to, greater than or equal to. That open circle, closed circle is going to help us in terms of writing our solution at the end of whether or not we're going to include those points. So now you've set up your sign chart, you're going to test any value in each of those intervals to see if the function is positive or negative. Again, because we've set up our polynomial to be related to 0, we're going to know if a particular interval is included by whether or not it's greater than 0 or less than 0. So that's why we only need to know whether it's positive or negative. This is easiest to do when you've got your polynomial factored, which is why we're doing that in step 2. And then you're going to choose the intervals that make the inequality true. So solve each inequality, write your answer in interval notation. We have the inequality 3x minus 1 times 5x minus 2 is greater than 0. So we've already set the inequality to 0. Step 1 is done. Step 2 would be to factor. This is already factored. So step 2 is done. The next point is to find our zeros, or the critical points. So our critical points are where each of those factors equals 0. So that's going to be positive 1/3 and positive 2/5. Again, if you need to set up those equations in the margin, go for it. You might feel very comfortable solving those equations in your head, though. So now I'm going to set up my sign chart, marking my critical points. Now, 1/3 and 2/5, it might end up helping you to look at a decimal of that. So 1/3 is approximately 0.333, and then 2/5 is 0.4. And that might just help you in terms of placing them on your number line and also identifying values in each interval. So we've got 1/3 is less than 2/5, so we want to make sure it's to the right of or to the left of 2/5. Because we have an exclusive inequality here, the greater than, strictly greater than 0, we're going to have open circles on both of those critical points. And now we need to figure out a test point in each of these intervals. So there's 3 intervals. There's one here, values less than 1/3, one here, values between 1/3 and 2/5, and here, values greater than 2/5. So a number less than 1/3, pick something easy. I'm going to pick 0. A value between 1/3 and 2/5. Knowing those decimals is going to help me. I'm going to pick 0.35. You could put any value though. You could put 0.34. You could do 0.33895. Really, it's up to you. Try to pick easier values though. That's going to make the next step even easier. And greater than 2/5, I'm going to pick x equals 1. So now what I'm going to do is I'm going to take that test point and plug it into my factored form, which was already given to us. If I plug in 0 into my first factor, I end up with a negative number because 3 times 0 minus 1 is going to be negative. I don't need to process what it actually equals. I just need to identify whether it's going to be positive or negative. My second factor, when I plug in 0, is going to be 5 times 0 minus 2 is also going to be negative. Now these two factors are being multiplied. The product of two negatives is a positive. So what this tells me is that any value less than 1/3 is going to end up with a positive function value. This is going to be greater than 0. Okay, we're going to do the same thing with x equals 0.35. This one's going to be a little bit trickier. When we're dealing with decimals, it's always a little bit harder. So 0.35 plugged into my first factor is actually going to be positive because 3 times 0.35 is going to be greater than 1. And then 0.35 in my second factor is going to be negative. And then the product of a positive and a negative is negative. And then plugging in x equals 1 into my first factor, that's going to be positive. X equals 1 into my second factor is also going to be positive. And the product of two positive factors is positive. So I've completed step 5. Step 6 is choose the intervals that make the inequality true. What we're trying to find is where this inequality is greater than 0. So that's where we have a positive function value. That's going to be here and here. And we can write our solution in interval notation. The first shaded region is from -infinity to positive 1/3. We're not including either of these. Remember, 1/3 has that open circle, which means that we'll use a parenthesis. Union 2/5 to positive infinity. Again, 2/5 also has a parenthesis. For x squared minus 11x minus 3 is less than or equal to 0. That first step is done for us because it's already set to 0. So now we're going to try factoring. Again, thinking about the options for finding our zeros or factoring, we do really want to try to factor this because it's going to make the rest of our work a lot easier. So if you want to use trial and error, you want to use the AC method, that's up to you. But looking at my coefficients of 4 and 3, they're pretty workable. So I'm going to just go through trial and error. So I'm going to start with 4x and x, and then I have factors of 3, which is 3 and 1. I can already see if I do 3 and 4, that's 12, and then 1, I might be able to work to get to 11. Now I just need to pay attention to the signs. So it's the factors of negative, or they're factors of -3. So one is positive, one's negative, but we want them to combine to give me -11x. So I really want a -12x and a positive 1x to get that -11x in the middle. From here, finding my critical points is setting each of those factors equal to 0. So we're going to get -1/4 and positive 3. Setting up our sign chart, -1/4, positive 3. Because this is an inclusive inequality, the less than or equal to, we're going to have filled in circles here at both of these. because our solution is going to include when it is equal to 0, which is the -1/4 and 3. Our test points, something less than -1/4, we're going to plug in -1. Between -1/4 and 3, x equals 0, and more than 3, x equals 4. Again, there's a lot of options for your test points. I'm trying to pick very obvious, easy test points to plug into my factors. So plugging in -1, -4 plus 1 is going to be negative. -1 minus 3 is going to be negative. The product of two negatives is positive. Plugging in 0 to our first factor, 0 plus 1 is positive. 0 minus 3 is negative. The product of a positive and a negative is negative. And then plugging in x equals 4, 16 plus 1 is positive. 4 minus 3 is positive. The product of two positives is positive. Now we're trying to find where this is less than or equal to 0, so we're looking for the negatives. That's going to be in that middle interval, which is from -1/4 to 3, and we are including both of those endpoints.